more kind of narrowly. Oh, I see that.
You're live now.
Microphones are turning on. And specifically, I will be talking about oral absorption. This will be a focus of my presentation. So, but when I start presentation, I usually like to give a definition of what I will be talking about and what I mean by certain terms. So, absorption is related to mass transport of drug compounds from gastrointestinal tract, if we talk about oral absorption, through the membranes into the blood circulation. So if we put this in a kind of mathematical terms, so we need to integrate over the area available for absorption and over the time which is available for absorption, the flux of compound and the flux of compound through the gastrointestinal walls. They will depend on location, and by location I mean it was a duodenum, jejunum, and why it's dependent on location, because location may have different pHs, may have different medias, was mentioned by other speakers, so it may affect the flux. And how it could affect the flux we will see in my follow-up slide. So, and also it can depend on the time when concentration of the drug changes over time, so as the flux also changes. So in the most complex thing, if only we can know the flux of the drug in each particular area of gastrointestinal tract, we would be able to perfectly calculate what would be a mass of drug absorbed. However, it's not the case. Okay, so let's take a little bit of, or dive a little bit more into this formula and see what is the flux. So flux is a measure of transport. It's the net number of moles of particles crossing the unit area per unit time, which is perpendicular to this unit area. So it's a rate of a drug absorbed per unit area per unit time. Again, mathematically, if we write it down, and I'm sorry for probably a little bit too much of the mathematics here, but it's just a definition. So it's a mass of the drug per area per time, but we usually work with concentration. So in order to translate it into concentration, we need to introduce the volume multiplier. So this is from definition, and from the Fick's first law, it's actually a product of effective permeability of the drug through the membranes times the concentration of the drug, which is present in the gastrointestinal tract. Now, when people are trying to modify the absorption or to improve absorption, they very often focus on the modifying the concentration, the dissolution rate, supersaturation properties. They provide these different formulations which increase the concentration of the drug. But very often it has been shown in the literature that different excipients, they actually also affect the effective permeability. So they can change the permeability through unstirred water layer, for example. They also can change the partition coefficient between the aqueous media and the membrane media, and partition coefficient is directly related to transcellular permeability of the drug. So, and I will try to kind of emphasize that it's important to look at the combination of these two very important characteristics together rather than in a separate investigations. So, and this is a slide I'd like to represent. It's not our work, it's from a publication of 2012 of a group of Japanese scientists. When they did this dissolution permeation device. So on one side they had a dissolution chamber divided from the permeation chamber by a Keiko-2 monolayer, similar to what Sid was showing earlier in the day. So they had a danazole, which is a very low soluble compound, and they had had several different formulations of danazole. So if you look at the left, you could see that the highest amount of compound dissolved after 2 hours was from a particular lipid-based formulations. But on the right side, we see a concentration versus time profile in the receiver compartment. So we can see that from this, the highest amount dissolved, it wasn't the highest amount absorbed in the receiver chamber. So it was number 3 or 4. And the highest amount absorbed in the receiver chamber was from the formulation, which you, if you only had done your dissolution study, you probably would dismiss this formulation as not is not of your first choice, obviously, because from the amount of drug dissolved, it was number 4. So this kind of emphasizes that changing the formulation, you can affect the amount of drug dissolved. However, different formulations will also affect how fast this drug can penetrate through the membranes. So several years ago, Pion introduced a device which we called microflux. And this is a very similar idea to the Austin chamber, which again was introduced previously. So what we have here, we have a donor compartment when we can introduce our formulation or drug, and it's usually small volume, so this particular device is used early in the early development or discovery stage. And we usually actually over here try to simulate the intestinal condition. So very often we would start with a simulated gastric condition at pH 1.6, would do experiment there for about 30-45 minutes, and then we would shift conditions from a gastric condition into fasted state simulated intestinal fluid. So the receiver chamber always have pH 7.4 and has this zinc component, which is similar to BSA, but it's another chemical. And what's even more importantly, sometimes in both chambers we have a fiber optic probes which can monitor concentration of the drug simultaneously in your dissolution and in the receiver chamber. And device can place 4 of these pairs simultaneously, so you can do your experiment in parallel. So you can either do different formulations and compare them, or you do just more statistics and then do different formulations in the different experiment. So this device allowed us to combine the benefits of in situ concentration measurements available with fiber optic device with this dissolution / permeation experiments. Well, so I'd like to show a couple case studies which were done using this device. They're not a full range, but just to give examples. So we had a case study, we had a research compound. Unfortunately, we did not know the structure. We did not know what was the nature of this compound. It was a client compound, and client wanted to evaluate this device to see if they can find any use of that. So it's a research compound. We did experiment, as I explained to you. We started in the SGF, or simulated gastric fluid, for 30 minutes. After 30 minutes, we shifted the media in the donor to FaSSIF, and then see what happens. So this is a concentration. So we had one compound, we had 5 different formulations. So the client wanted to see which formulation would be the best one. So from the dissolution study alone in our donor compartment, we could clearly see that there are 2 winners, 2 formulations were providing the highest concentration. However, if at the same time we looked at our receiver chamber, only one of these 2 formulations was highly permeable, or it was absorbed the most. And the second formulation, which acted very nicely in the dissolution study, they actually was among the bunch of the other formulations. So what was interesting, it was a feedback from the client, because when we did this study, we had no idea whether we picked it right, whether we picked it wrong, so we just provided the results back. And we were told that this formulation which we selected was the best formulation acted in the dog model. So it was very encouraging to us. So another study I'd like to present was with collaboration with our colleagues from Novartis in Basel, Switzerland. And we started with available in vivo data with rat studies where different formulations or several formulations of itraconazole were compared together. And they were nanoparticles. So with crystalline itraconazole, yellow line, there was nanosuspension, which is this purple line. There was a commercially available itraconazole, which is Sporanox. And then there is also amorphous solid dispersion with Soluplast, which is a BASF polymer, if you know. So our colleagues from Novartis wanted to know, can we do this kind of rate or ranking of these formulations just from this relatively simple experiment? So we did our microflux experiment, and we measured both flux and also accumulated amount of itraconazole after a certain period of time, which was 4 hours. We selected that, and we could see that there was two clear winners, Sporanox and Soluplast, the same as our colleagues see in the animal study. And nanosuspension, although it was better than crystalline itraconazole, it was much worse than amorphous solid dispersion or commercially available formulation. Then when we plotted this against each other, when on one axis we plotted AUC data from in vivo study, and on another axis we plotted AC sort of the data or accumulated mass data from our in vitro study, we not only see the ranking, we actually were pleased to see that this is a very nice linear relationship between these two. That's indicated to us, at least for this, again, for this case, I cannot generalize, but for this case, we probably, if we had some other formulations, it would be interesting to see whether they would be on the same line. So we published this data very recently. If you're interested, you can ask for a reprint of this paper. So, and in terms of itraconazole, this is a very low soluble compound, and it's kind of a perfect model drug for multiple groups. And I'd like to show another study from our colleagues from Band Research, now Lonza, where they also studied itraconazole with a flux device, their modification of the flux device. And they also saw that the relative flux increase was correlating with rat in vivo data. Well, so this is, as I showed it, it's a very small volume, and many people are working with the final drug products. They work with their final formulations with tablet capsules. So, and we were immediately asked, can we do this kind of study, but now not with their suspensions or powders or solutions, but with the final products. And we introduced so-called macroflux, where we just put the absorption chamber in the USP apparatus. And initially we put it in the standard USP apparatus when we could work with volumes 800, 900, 1 liter. But by now we also can do it like in the miniaturized USP vessel, when we can work with a more biorelevant 250 milliliter volumes. So the idea is the same. We have fiber optic probes which can monitor in the real time both dissolution and permeation. And we try to work with biorelevant media, biorelevant pHs, in order to simulate as best as we can the in vivo conditions. Well, with this device, one of the first application we were doing with the help of an intern student from Europe. She was interested to see if we can separate different formulations, brand name and also generic formulations of telmisartan. And the reason she was interested because she knew that one of the generic formulation of telmisartan had issues, had difficulties when they were going through bioequivalence studies. So she wanted to know if we test this with macroflux, can we pick up these potential issues before going to the human studies? So we, as you could see, we gathered as many generic telmisartan formulation as we could. And then we grouped those formulations based on the inactive components which those formulations had. Some of them use sorbitol, some of them use lactose, some of them use mannitol. And what was interesting that the formulations which use mannitol actually had some issues, in a particular one, telmisartan actavis. So what we saw there is that when we studied based on our flux value, we saw that actavis had some issues, and this was exactly the issues which were mentioned in application of these formulations to FDA, and I don't remember actually it was FDA or it was European agency, and the manufacturers had to argue why this would still be okay, and eventually this formulation was accepted, but it was on the borderline. So another next study we had with our colleagues from Genentech, and they wanted to know if this device could be used to first of all predict drug-drug interaction from pH-modifying agents. Namely, if you have a weak basic drug which relies on full dissolution in stomach, but together with this basic drug, you take some pH-raising drug like famotidine or ranitidine, so your stomach pH would be higher, so drug will not be able to fully dissolve. How much effect it will cause on the full absorption of this drug or bioavailability of this drug. So we developed a method when we first start with a normal gastric condition at pH 1.6, and then we translate them into the FaSSIF, and another set of the parallel assay, which everything would be the same, but our stomach conditions would be alkalized, so they will be at pH 4.0. And we would do the same experiment now with starting from pH 4.0 and translating into or converting it to FaSSIF at pH 6.5. And again, fortunately for us, our colleagues had in vivo data. So we were not only able to do our in vitro study when we clearly see for first of the drugs where strong drug-drug interaction was expected, we also saw this very strong drug-drug interaction in our in vitro assay. And more importantly, we saw that we detected about 90% reduction in flux and absorbed amount from in vitro assay, and it was about 80% reduction in AUC due to drug-drug interaction in dog PK studies. So it was, again, what was very kind of encouraging to us, that it was not only qualitative comparison, but also quantitative data was quite relevant. And then we moved to another drug, which both of them are class 2B drug, BCS class 2B drugs, where this drug was specifically formulated to minimize the drug-drug interaction from acid-reducing agents. And we also see much less effect of this acidifying of gastric condition before converting them to FaSSIF. And again, in terms of the quantitative results, we saw that 25% reduction in the total amount in vitro, and it was about 25% reduction in AUC area in vivo, which is also very encouraging to us. So this work has been very recently published. So if you are interested in the more details of the study, please let me know. So this is ongoing. Again, itraconazole is taken as a model drug, and we are trying to investigate if this device would be useful for food effect. So we had, again, now several commercial itraconazole formulation. That's Sporanox capsules, but Sporanox is also formulated as a solid cyclodextrin-based solution. And there is also another generic drug, at least on the European market, which is a half dose, but they claim the same biorelevance or the same availability of this drug, despite of the half the dose. So we we're evaluating our reduced volume device. When we started with 200 milliliter of gastric media, and then we would convert it to 250 milliliter of FaSSIF, or as it was in this case, we were not interested in conversion, we were more interested in doing this experiment first in FaSSIF and then in fat state simulated intestinal fluid and compare results. So which was interesting, if I will try to point out that as expected from the in vivo, it was a positive food effect for solid formulations, for capsules of both Sporanox and Lozanox, but the solution had a slightly negative effect, and it was exactly what was reported from the in vivo studies. It was positive food effect for capsules and slight negative / no effect for solutions. Moreover, we were able to predict that our absorption from the solution would be much higher than absorption from the solid capsules. And also we were able to not only, again, qualitatively or rank ordering, but also quantitatively predict this effect. So this this is still work in progress, and this is very encouraging to us. All right, so I showed you some application of the flux measurements. Mostly so far we saw how we can apply them as a kind of comparative study between different formulations, but can we use these flux measurements in some kind of prediction of absorption? Because if you are asked whether your compound is low soluble or highly soluble, and you are told certain number, you would understand, is it high or low solubility? The same with permeability. We have seen several cutoffs, 5, 10 to the minus 6 centimeter per second. Let's say, I guess this is in Keiko2 or some other values. So can we use flux for this kind of measurements? So in other words, can we use flux to do some in vivo, in vitro simulations? But before we go to this, I'd like to give a definition. What do we understand by in vitro, in vivo correlation? And I pulled out two definitions. One is from USP and one is from FDA. And they're actually quite different. So you can read them, but basically USP says that establishment of rational relationship between a biological property or a parameter derived from biological property produced by a dosage form and physicochemical property or characteristic of the same dosage form. So this would constitute in vivo, in vitro relationship or correlation. So it's a rational relationship, while FDA emphasizes that IVIVC is a predictive mathematical model describing the relationship between in vitro property of a dosage form and a relevant in vivo response. All right, not to be disrespectful with the host of this meeting, but I like the FDA formulation a little more because I can relate to what is mathematical model, what is a rational relationship is a subject for more discussion, I'd say. So I selected this one. So what it means, so a mathematical model, we have in vitro property, what property? But let's say we measure something. It could be solubility, permeability, flux, whatever measure. We put it in the black box and how transparent or intransparent this box, this black box is up to you. And then on the end, we get in vivo response. So we had several talks today from Simulation Plus and from SimSip, where showed the use of this black box, which is our very complex mathematical model. Well, the holy grail of in vitro assay, if in vitro property is approximately equal to in vivo response, that would be great. Sometimes it's very difficult to get. Anyway, so this is our goal. How we're going to achieve this goal? So this is real man's. We'd like to get the main properties which would be affecting the absorption. And we're looking at the gastrointestinal tract, we look at the pH, intestinal media composition, volumes, area, transit time. These are all key characteristics. So we need to at least somehow gather those. And we're looking at small intestine, duodenum, jejunum, ileum. So well, we can try to kind of mimic it one-to-one, which will be a quite expensive proposition. However, we already had some talks which refer to this model. It's Team 1, I believe. So anyway, so this is a useful model. I don't argue about this, but is it a very practical model? So you create all this complexity. Is it always necessary? Well, can we come up with a more robust predictive model which will be easier to understand? And sometimes if we need to go into the more complex model. So if we can go from real man to some kind of absolutely cylindrical man, which has a very nice cylindrical stomach and a very nice cylindrical intestine. So we can actually do our integrations, which I showed in the very beginning, much, much easier. Well, how we can kind of employ the absolutely cylindrical man? I showed that the mass absorbed would be integration of flux through area and through time. So let's assume that flux doesn't change. When it happens, for example, if you have solubility limited absorption. When dark is always in equilibrium with its solid form, and it's not supersaturating and it's not precipitating. So just start with a very simple. In this case, you can easily integrate this, and then the mass absorbed mass will be flux times area of the small intestine, or area available for absorption, times transit time. All right? So for solubility, permeability limited cases, if we want to calculate fraction absorbed, which is mass absorbed divided by dose, we can do this very interesting and simple trick. We can divide both numerator and denominator by a volume of small intestine. So then in numerator we have flux, we have area of small intestine divided by volume of small intestine times transit time, and in the denominator we have dose divided by volume of small intestine. Well, for the absolutely cylindrical man, our friend in this case, area of small intestine to the volume of small intestine is just a cylindrical problem. It's a 2 divided by radius of small intestine. So if you, again, if you consider the radius of small intestine to be 1.5 centimeters, that's very easy. Now, dose divided by volume of small intestine, again, if we consider 250 milliliter is our some kind of a magic volume, then it's also, again, very simple. You divide your dose by a volume or by 250 milliliters. Well, let's see how it can be used in practice. So this is from the study I showed previously of itraconazole, and I show there this red bar is a sporanox initial flux. So let's say that this flux stays intact, that itraconazole does not reprecipitate, and it just constantly has this flux. So very easily we can plug in all these values in the formula I showed previously, which is flux, area to volume, transit time, which is 3.5 hours. Again, this may or may not be relevant time. And then it's divided by dose over the 250 milliliter. We get 43% absorbed for itraconazole. which is from very simple, very intuitive calculation, is actually not a bad number. Well, we did it for a couple formulations, including itraconazole, and I tried also to show what is a reported absorption value. For example, for Micardis, for telmisartan, the reported fraction absorbed is 90%. We get 100%, so we a little bit overestimated. For Sporanox, the reported fraction absorbed is 85%, and we calculated 43%. We undercalculated, but itraconazole is a drug which is bind to all tissues. It actually, I think it Tmax is like 5 hours. So we cannot calculate a fraction absorbed based on 3.5 hour estimation of transit time. So the transit time must be taken into account much longer than 3.5 hours.
Dr. Tsinman, 2 more minutes, please.
Perfect, thank you. So this is how we would use this. So, and at this actually I'm coming right into the conclusion. I just like to, I hope I at least, if not convinced you, but give you some idea that flux assay, they allow investigation of complex formulations and building realistic pharmacokinetic predictions. Introduction of absorption chamber into dissolution setup leads to more biorelevant dissolution studies. That's relatively simple and robust flux measurements can provide great in vitro tool for capturing major factors to absorption, leading to, again, more realistic IVIVC. And that complication of in vitro models does not necessarily mean that better IVIVC can be achieved. So this, I would like to acknowledge my colleagues from Pion and from industry and academia who took a great part in multiple research and collecting data and helped me a lot with this presentation. And thank you very much. Would be happy to answer your questions.
Questions for Dr. Tsinman, please. Use the microphone.
Hi, I'm Xavier Pepin, AstraZeneca. Thanks for the nice presentation. I had a question regarding the cases where the model would fail, because you've presented nice case studies where the model works. And so, in your opinion, does the model always work for BCS class 2? Or does it work for BCS class 3 and 4?
Thank you for the question. The model, the reason the model works very well for class 2, because the permeability model, which is behind that, actually was initially developed to correlate with human jejunum permeability published by Leonard's group. So, and that's why in the class 2 compounds that the main barrier is the aqueous boundary layer for the permeability. The model usually, at least in our experience, works very well. In the class 3 compounds, the model, I think, where permeability limited, the model, it may work okay, however, because the permeability would be quite slow, it's not be that informative. So for class 3 and 4, we're investigating now the different membranes which we could use, so that would not be very slow, rate limiting steps.
Question here.
Yeah.
Dhaval Patel from Bristol Myers Squibb. So, very good presentation. The flux measurement, right? So, does it take care of the sink condition? Like, because, you know, when we do the in vitro release experiment, sink condition is always a barrier. I think your setup, does it take care of that? And then second question was about your data comparison between bioflux and macroflux, and I noticed that bioflux was more accurate than macroflux in one of the case studies, and if you could talk about what was the reason behind that.
Okay, thank you. So the sink condition, that's a very good question. So, and because we have in vitro system, we don't have flow to again simplify the system. We try to reach sink conditions by the use of the binding chemical. So in our receiver chamber, we have a chemical which can bind compound, preventing the backflux and preventing the equilibration or concentration equilibration of this compound. So we can reach much, much higher concentrations in our receiver chamber than we have in donor chamber. Obviously, eventually it will break, but we demonstrated that we can do at least 3-4 hours experiments where we still have syn conditions, so we still have linear increase of concentration. So your second question was a relation microflux and bioflux. It's not the matter which gives you they all produce, if you only measure permeability, they would give you the same answer. The bioflux would allow you to put the actual capsule or tablet in your vessel. So you can not only study some suspension, for example, or like miniaturized tablet, you actually will be able to study your final dosage form. So that's the main difference. When you try to recalculate it back to permeability, they're the same. So it's more what kind of form of the drug you are working with.
So I think my question was about one of the case studies. I'm thinking of one of your last slides. You had predicted fraction absorbed.
Okay, that's a good question, because initial study was done in 1,000 milliliters. So we had more diluted compound, means we had less concentration. So it underestimated the flux of the drug. And that's why it produced like 53% versus around 100%. So I think that was the reason.
So the volume was
critical. The volume was the reason. So 1 liter is not quite biorelevant volume.
Thanks.
Time for one more, or are we done?
Is it quick? 60 seconds, please, so we can stay on task.
Hi, Talia Flanagan from AstraZeneca. I'm doing the excipients presentation tomorrow, so naturally I was kind of drawn to your example where you had different generic formulations, and you'd pulled out the excipients, but I'm not sure whether you were saying that that was the reason for the difference in bioavailability. I wondered whether you could comment on the formulation that had mannitol in that showed borderline results in the bioequivalence study. What do you believe the mechanism was behind that? I'm asking because the mechanism by which mannitol usually affects bioavailability, your system can't mimic that because it's to do with transit and also luminal volume. So what do you believe was going on there?
That's a very good question. So I probably not ready to answer that yet. But from our purely PhysChem point of view, why excipient can affect that? It can, again, it can change the partition coefficient between the medium, aqueous medium, and the membrane. That's one possibility. The second possibility, it can interact with drug, it can bind drug more than other excipients. So this is another possibility. But I probably won't be able to answer your question, what was the reason here, although we did see it. Seems to be, at least with one formulation, not with the other, but with one formulation which used mannitol instead of original excipient, that the flux was lower and it was about the same. So if you think that Cmax divided by Tmax is some kind of analogous of your flux, it was exactly the same reduction what we saw.
Okay, thank you.
All right, Dr. Tsinman, if there are any other questions, can we hold that till after the final scheduled speaker, please? We'll have an open session. Thank you, sir.
Thank you.